Hi everyone. This section is the last bit of content for our upcoming exam. The section is titled the Mean Value Theorem. It actually includes two theorems for us to take a look at and to apply. The first is called Rolle's Theorem, and the next is called the Mean Value Theorem. Now, Rolle's Theorem actually relies on a theorem that we just saw very recently in the previous section, which was called Fermat's Theorem. Okay, so Rolle's theorem relies on Fermat's theorem. Okay. And then the mean value theorem, the proof for the mean value theorem, that is, relies on Rolle's theorem. Okay, so there is a progression here. Fermat's theorem was the one that we saw in the maximum and minimum section, where if we had a function that was continuous and smooth meaning that it is differentiable, so if it's continuous and differentiable, and if it had a local min or a local max within that interval, so for instance if we had a function like this, maybe on a closed interval, but if we knew that it had a local maximum, so that's somewhere within the interior of the interval, Fermat's theorem said that the derivative of the function at that point had to be 0. Okay, which geometrically means that the slope of the tangent line would have to be 0. Again, that requires a couple of things. That we are within an open interval so that we can define the derivative from the left and the right. Okay, it requires that the function is differentiable. So a maximum, it is possible for a local maximum to exist. If we didn't have differentiability, we could have a corner there, for instance. It would still be continuous and have a maximum. Okay. But we need the derivative to exist in order to get the conclusion of Fermat's theorem, which is that the derivative itself, when evaluated at the input there, it would equal 0. And of course, geometrically, that is interpreted as the slope of the tangent line would equal 0. Okay, so we rely on that result. It's similar for a minimum. If we had a local minimum, it would be the same result for every local max and local min within this interval. Fermat's theorem says that the derivative is equal to 0 at each of those. So Rolle's theorem is going to say that if a function starts and ends at the same y value, and if it is continuous and differentiable within that interval, then there is a guarantee that somewhere within the interval there must be a point where the derivative is equal to 0. Okay? We're going to have to verify the conditions of these theorems before we actually apply them in exercises for this section as well. The mean value theorem, well, mean is referring to average, so the average value, and the average we'll be talking about here would be the average rate of change. The mean value theorem states that if there is a function that is continuous over a closed interval and smooth within the interior, that is smooth over an open interval, okay, continuous and smooth, right, whether it is a linear function or one that just has a single max, or maybe arches out and has a single max up there, or a min, or some combination or whatever. Okay, the mean value theorem states that if we establish the slope of the secant line, that is the average rate of change, the slope of this line here would be the average rate of change. There's our mean. Okay. The average rate of change is the slope of this line. The mean value theorem is going to say that on the curve between these endpoints, somewhere in the open interval, there is at least one point such that the tangent line would have the same slope as this secant line. Okay, so geometrically, that is to say that there has to be at least one point within here, within this open interval here, okay, such that the tangent line would be parallel to this average rate of change secant line right here. Okay, so the slope of this line here is going to be found by taking the derivative, like f prime of c. Let's say f prime of c1, because that would be one such point where that would be the case. Okay. The slope of this tangent line is the same as the slope of that secant line there, connecting those 2 points at the end points. Okay, and for this graph that I've shown here, in fact, there would be another point, probably somewhere around here, which also would have a tangent line, and the slope of that tangent line, although we would have a different value of c, putting us there, so I'll call it C2, the derivative at C2 would also equal the same value of m. So each of these three equations are associating the same slope. They're all parallel to each other. So the mean value theorem, the mean value theorem is a theorem that guarantees by the conditions of continuity and differentiability within the open interval, okay, that there are going to be points, okay, whose such that the derivative at the point is the same as the average rate of change over the interval. Okay, so the mean value theorem is again is a continuation of Rolle's theorem. We'll see how that is, all right, how that applies. And Rolle's theorem is provable by using Fermat's theorem. Okay. And I mentioned already that for these exercises, you're going to be asked to verify the conditions and then apply the theorem. So for instance, for Rolle's theorem, you'll see exercises that state, let's take a look at the homework right here. You can see what I mean. Okay. The exercises say, in WebAssign, as well as right from the textbook, as well as on the worksheet I give you, as well as on your exams, for instance, verify the function satisfies the hypotheses of Rolle's theorem on the given interval. Then find all numbers C that satisfy the conclusions. On WebAssign, you only need to enter the values of C that are appropriate, and that end up satisfying the conclusion of Rolle's theorem, even though it does ask you to verify that the function satisfies the three hypotheses. So I want to make sure that you pay attention in the typed lecture notes and in a couple other exercises they'll do here in the video, that we're very specifically verifying that the function satisfies the three hypotheses. It's not enough to just say it is verified, therefore let's do the problem. Like, you have to actually demonstrate why you know that the conclusions are verified. Okay. The conclusions are again very similar to the conditions. The conditions are very similar to the conditions for Fermat's theorem. That is, we need to have a continuous function, and we're going to have differentiability on an open interval as well. There is one more condition that we're going to need for Rolle's theorem other than continuity and differentiability, and that is that the y value would need to be the same at the starting point and the ending point. That's for Rolle's theorem. For the mean value theorem, the y values at the end points can be different than each other. It doesn't matter. All right. Okay, so here are the theorems, okay, in your typed lecture notes, as well as you could find in the textbook, for instance. Okay. So for Rolle's theorem, suppose that f is continuous on a closed interval, so that includes the endpoints, and that f is differentiable on the open interval from a to b, right? So we're not including differentiability at the endpoints, but as the third condition of Rolle's theorem, suppose that the endpoints have the same y value. Okay? So like I've shown here. So imagine that, whatever the y value is at the starting point, you move continuously and smoothly through the interval, and you end up at the same y value, right? So that could mean that you do so through a max. It could mean that you do so through a min. It could mean that you're dealing with a constant function, where the y value is still the same at the beginning and the end of the interval. It could mean that you're doing some kind of undulating, like a trigonometric function, for instance, as long as the y values are the same at the beginning and the end. But it must be smooth within the interior of the interval. That is, it must be differentiable within the interior. Okay, the open interval a to b. Okay, if these conditions are satisfied, these three right here, then this is an existence theorem now, like we've had with Fermat's theorem. Then what exists is there must be a number c. In fact, there can be more than one number c in the open interval such that f prime of c is equal to 0. Okay. Back to these little sketches over here, we can see from this picture here, right, this is continuous and smooth. There is a single point in here that we can see geometrically the slope of that tangent line would equal 0 because it has a maximum. Okay, there would be a single point here such that the slope of the tangent line there, it would be 0 because that's a minimum. All right, f prime of c is equal to 0. For the constant function, because it's constant, every single point of which there's an infinite amount of them, at every single point, the derivative is going to equal 0 because it's the constant function, right? It's constantly has a slope of 0. And for something like this, again, for every maximum and minimum, since the derivative exists at every single one, and for every one of these local maxima and local minima, that is, okay, the slope of the associated tangent line is going to equal 0 as well. So f prime of c at each one of the inputs c here, they would all equal 0. Okay. So these are different types of possibilities we could have: a continuous and smooth function on a closed interval where the y value at the start and the end of that interval are equal to each other. So we can see from that picture there why it is reasonable. Okay, why it is reasonable that f prime of c would equal 0 there. I'm actually taking a look at the classwork here. All right. Okay, here we go. We're back to the type notes over here. Okay. All right, because I go a little more in detail here in the type notes. I'll give you my interpretations of this, how you can interpret it in terms of the context of a derivative and geometrically as well. Okay, so if we have a continuous and differentiable function on an interval with equal outputs, that's the y values, then there must be a horizontal tangent somewhere within the interval, and it could happen at more than one point, as was already demonstrated a moment ago. Or in other words, b, it must have an instantaneous rate of change, our interpretation of the derivative of 0 somewhere within the interval. So here's an interpretation in terms of an application for that. Consider this scenario. Suppose that there's a vehicle on the road, okay, and its velocity is measured at some time, let's say noon, and then its velocity is again measured at 1 p.m., an hour apart. And suppose that the velocity is the same at both of those times. Well, by Rolle's theorem, it would be, since we have, okay, we're dealing with the function now of velocity. Velocity is continuous, it changes continuously. It is differentiable as well. And we have that the starting velocity is equal to the ending velocity. At the velocity at noon, the velocity at 1 p.m. are the same velocity. Rolle's theorem guarantees, therefore, that there must be some moment in the open interval, that is, there must be some time, at least one time, between noon and 1 p.m., such that the derivative was equal to 0. And what's the derivative of velocity? The derivative of velocity is acceleration. So that means by Rolle's theorem, we can assume that the vehicle must have had a 0 acceleration for at least some time between noon and 1 p.m. It could have been at several times, but at least at some time it was traveling at what would be a constant velocity, even instantaneously at a constant velocity. That is, it could have been accelerating and decelerating, accelerating and decelerating, okay? But there would have to be at least one time in that interval, okay, whereby the acceleration was 0, so that the velocity wasn't changing, at least instantaneously. Okay? So that's one interpretation. We also have geometric interpretations, which we can use in establishing a method for finding out if a function is, by use of the derivative, is actually increasing or decreasing over an interval over the real number, and we'll use that in a future section, so that we can have a technique in order to determine where functions are increasing and decreasing. We'll take a look at that in the next section, though. All right, now the mean value theorem has conditions that are quite similar, but notice it has 2 conditions instead of 3. Okay, the mean value theorem also requires that we have a continuous function on a closed interval, and that we have a differentiable function. The same function is differentiable on an open interval. Those are the same. All right, the same 2 conditions that we started out with Rolle's theorem. But for the mean value theorem, the starting point and ending point don't have to equal each other. It doesn't matter what the y values are at the beginning and the end. Okay, they can be different from each other. Okay. The conclusion we get from the mean value theorem is, again, as I've already shown geometrically here, okay, is that the slope of the secant line connecting the end points of this interval, that is the average rate of change over that interval, okay, is the same as the instantaneous rate of change at least one point contained within the interval. And that's what this is stating. There is at least one number c in the open interval AB such that the derivative at c, that's the slope of the tangent line, is equal to the rise over run between the endpoints. So this would be average rate of change. Okay. An equivalent way to make this statement, just multiply by b minus a onto both sides, is to state this. So this is the same statement, and this can be useful for saying if we wanted to find a net change, where net change is just the difference in the y values, we can determine the net change by taking the product of a derivative at some point within the interval times the length of the interval itself. Okay, and we know that these are going to be equal to each other for some value of c within the interval. Interpretations. Okay? A continuous and differentiable function on an interval, A, has a tangent line parallel to the secant line over that interval. Or B, interpretation. Somewhere in the interval, the instantaneous rate of change will be the same as the average rate of change over that interval. Okay. Let's take a look at the proof for Rolle's theorem. With proof of Rolle's theorem, I mentioned it relies on Fermat's theorem. And Fermat's theorem, again, states that if the function has a local maximum or a local minimum, so that must be within the open interval, okay, then the derivative at that local max or local min must have equaled 0. Okay, that was proven in a previous section. Okay, so I showed the different combinations, the different possibilities we have for when we are choosing the two endpoints to be the same y value. Notice in each one of these, the y value is the same at the beginning and the end. And then we have continuous and smooth curves between them, either constant, one max, okay, a max and a min, one min, and in all combinations we can see that there is at least one point, and on the constant function there's an uncountable number of these points. There's always at least one point where the derivative would equal 0, that is the slope of the tangent line is equal to 0. And that's sufficient to demonstrate that Rolle's theorem is valid. Now, how to solve exercises involving Rolle's theorem. Okay? And there's a couple steps we're going to want to follow. First, you're going to have to verify the hypotheses for Rolle's theorem on the interval. That is, state that the function is continuous on the given closed interval, and then state that the function is differentiable on the given open interval. That's the same interval but without the endpoints involved. But you have to say why it's continuous and why it's differentiable. Refer back to a previous section when we talked about continuity. We established that there were families of functions that were continuous over their domains, for instance, and we can create combinations of functions. Let's take this example. F of x equals x squared minus 5x plus 6. What family does that belong to? That is belonging to the polynomial family. Recall that all polynomials have the characteristic that they are continuous for all real numbers, negative infinity to positive infinity. So we can start to establish continuity here. We can say, well, f is continuous on the closed interval 0, 5 because f is a polynomial, and polynomials are continuous for all real numbers, or continuous on negative infinity to positive infinity. Furthermore, the interval 0, 5 is a subset of all real numbers, right? The interval 0 to 5 is contained within the larger domain of all real numbers. So therefore, this function is continuous. So state the family, state where that family would be in entirety, where that family would be continuous. Okay? This function is continuous for all reals. And then furthermore, state that the interval that's given, notice that the interval that's given, okay, is a subset of the interval where you've just stated it would be continuous. Now for differentiability, it's the same idea. Remember, differentiability, though, we're working on the open interval. Okay? We know that polynomials are, we established this before, polynomials are differentiable also for all real numbers. They are smooth functions over their entire domain. So since f is polynomial, it is therefore differentiable for all real numbers, or from negative infinity to positive infinity. And again, since the open interval 0 to 5 is a subset of all real numbers, then f must be differentiable on the open interval 0 to 5. Okay? So again, state the family and state where the characteristic, continuous or differentiable, where that would have been true for this member of that family. Okay, and then the third thing is to verify that the given interval that you're interested in is contained within wherever that statement would have been true. For continuity, we're using the closed interval. For differentiability, we're using the open interval. And the third condition of Rolle's theorem, that is that the y values at the start and end of the interval are equal to each other. So we check what is f of 0 and what is f of 5. So we use the function itself to find out what those are. We find f of 0 equals 6, and we find that f of 5 is also equal to 6. So since f of 0 equals f of 5, then we verified the third condition. F of a is equal to f of b. These three conditions are satisfied, therefore, by the reasoning that we've already established here, no matter what shape the function actually takes now, since it's continuous and differentiable, and the y values are equal, then there must be at least one value c in the open interval such that the derivative at c is equal to 0. That's an existence theorem again. Rolle's theorem tells us that the thing exists. In this case, that there is a point where the tangent line is horizontal, or that the instantaneous rate of change is equal to 0. Okay, but Rolle's theorem doesn't tell us how to find it. Okay, it tells us that it exists. But we know how to find it. We've just been given an equation here. F prime of c is equal to 0. To find it, we need to find the derivative of the function, plug in the value c, where c is just going to stand for the number or numbers that we're going to get as solutions, and then solve the resulting equation where that derivative is equal to 0. So, take the derivative. So that's find f prime of x. That would be 2x minus 5. Set 2x minus 5 equal to 0 by plugging in c. That becomes 2c minus 5 is equal to 0. Solve for all values of c. We get one value of c. C is equal to 2.5. One more thing to do that is an important step here before you submit this answer. Check to verify that this value is actually inside the interval we were interested in. Now, we knew that we were going to get at least one value within that interval because that's what Rolle's theorem guarantees for us. But we might have solved the resulting equation and gotten more than one quantity. It's important then to verify which of those quantities are actually inside the interval that we're interested in. Remember, this must be a value of c where the derivative is equal to 0. Right, the derivative is equal to 0, and we're only verifying differentiability on the open interval from 0 to 5, not the closed interval. So if one of our values from the derivative was either 0 or 5, for instance, we also would not include that because we're not verifying the derivative of this at the endpoints. Okay, so for the next example here, we have a different function, f of x equals the sine of 2x. Verify the conditions for Rolle's theorem. There are three of them: continuity, differentiability, and the endpoints have the same y coordinate. So for continuity, well, sine of 2x is the sine function composed with a polynomial, and the sine function is continuous on all real numbers. So since the given interval, closed interval 0 to pi, is contained within the set of all real numbers, therefore the function f must be continuous on the closed interval 0 to pi. Similarly, for differentiability, we know that the sine function is differentiable on its domain, that's all real numbers. In fact, all the trigonometric functions are differentiable within their own domains. So since the open interval 0 to pi is contained within the domain of the sine function, then the function f is differentiable on the open interval from 0 to pi. And finally, the third condition, evaluate the y coordinate at the endpoints and verify they're the same as each other for Rolle's theorem. F of 0 would be the sine of 0, and that's equal to 0. And f of pi is equal to the sine of 2 pi, which is also equal to 0. So f of 0 equals f of pi, so Rolle's theorem's conditions are verified. Therefore, we know that within the open interval from 0 to pi, there is at least one value we can call c, such that f prime of c is equal to 0. So Rolle's theorem gives us the existence of at least one of these values. And now we can go and find, can we determine what the values of c would be within that interval? So we can find out by finding the actual derivative of the function. So f prime is going to be 2 times the cosine of 2x, right? It's an application of the chain rule there and the differentiability of the sine function. Okay. And now if we plug c into our derivative, we'll get f prime of c, and then we can set that equal to 0 for Rolle's theorem. So we get 2 times the cosine of 2c equals 0. Divide by 2, that's the cosine of 2c is equal to 0. Now the cosine of, let's say, theta would equal 0. Okay. At what values? Cosine of theta is equal to 0 whenever theta is equal to pi over 2 plus k pi. And we can use, like, the unit circle is one way that I have for for visualizing this. When we're solving a basic trig equation for cosine or for sine, we can envision a point that's moving around the unit circle, and the coordinates of that point are telling us the sine or the cosine, okay, of the associated angle or arc length. Back to trigonometry again. Okay. Cosine of theta equal to 0, right, on the unit circle. Point moving around the unit circle at this point and at this point, the x coordinate is equal to 0. and the x-coordinate, okay, is equal to the cosine of theta, the y-coordinate is the sine of theta. We can also say the x-coordinate is the cosine of t, and the y-coordinate is the sine of t. Right? Again, that's where theta would be this angle right here in standard position, right? T would be this arc length along the circle. Okay, and theta and t are equal to each other when we are within the unit circle itself. All right, so some values of theta that would make this true. We could say, well, theta 1 is equal to pi over 2 plus 2k pi. Okay, or right, k times 2 pi, where k is any integer. Okay, and for the other point, we could say 3 pi over 2, we could say negative pi over 2, for example. Right? There's an infinite amount of those angles that would get us to this point. So negative pi over 2 plus 2k pi. Okay, but we can also combine these two solutions into one set. They're separated from each other by symmetry by pi. Okay, so we can say theta is equal to pi over 2 plus k pi. So then if we're solving an equation like cosine of 2c is equal to 0, okay, well, then we have that 2c is equivalent to our theta, where theta is pi over 2 plus k pi. And then we can solve for c. So c is equal to theta over 2, which is all this divided by 2, so a half of this. If we take half of this, we're going to get pi over 4 plus k pi over 2. Those are our values of c that satisfy this equation right here. All right, now we only want the values of c, though, that are in the interval from 0 to pi, in that open interval. So we don't want all the solutions. This would be infinitely many of them. Just the ones that are within this interval. And we can choose values of k to plug into our statement here to find values of c, right? We can choose k as any integer, 0, plus minus 1, plus minus 2, plus minus 3, so on and so forth. So for instance, if k is equal to 0, we get pi over 4. Pi over 4 is in this interval, so we'll take that. If k is equal to 1, we get pi over 4 plus pi over 2. Pi over 4 plus pi over 2 is the same as 3 pi over 4, and that's also in this interval, so we'll take that. If we take k is equal to negative 1, we would get pi over 4 minus pi over 2, but that gives us negative pi over 4. And negative pi over 4 is not inside this interval. If we choose k is equal to 2, we'll get pi over 4 plus pi, and that would give us 5 pi over 4, which is again outside of this interval. Okay? These are the only two quantities of c, right, that satisfy that the derivative of the original function is equal to 0 and where we are contained within this open interval. So these are the solutions that we have from the type notes. Pi over 4 and 3 pi over 4, the values of c. Okay. Let's try another one for Rolle's theorem from the start. Okay, so same two steps, although the first step really has kind of 3 steps in it. Verify the conditions for Rolle's theorem on the interval. Okay. Then find all values of c inside of the open interval. Okay. That satisfy the conclusion. Okay, to Rolle's theorem. All right, let's take f of t is equal to t cubed minus t plus 2. And I'll put this on the interval from -1 to 1, the closed interval. Okay, conditions, first of all. Conditions. Okay, first, continuity on the closed interval from -1 to 1. Okay. Okay, so we have the f is continuous on the closed interval -1 to 1. Why? Because f is a polynomial, okay, and a polynomials are continuous on all real numbers, -infinity to infinity. So -1 to 1 is a subset of where the function f would have been continuous. Therefore, f is continuous on that subset. 2. Differentiability. So diffable on the open interval from -1 to 1. Okay, so f is diffable, okay, differentiable on the open interval -1 to 1 for the same reason, okay, because it's polynomial. And polynomials are also going to be differentiable on all real numbers. All right. Okay, and the third condition for Rolle's theorem, check that f of a is equal to f of b. So we had a is -1, b is +1, and we're dealing with t cubed minus t plus 2. So we have f of -1, which is -1 cubed minus -1 plus 2. What is that equal to? -1 plus 1 plus 2, and that equals 2. And then f of 1 is equal to 1 cubed minus 1 plus 2. Right? That equals 1 minus 1 plus 2, which is equal to 2. Okay, so we have f of -1 is equal to f of 1. They're each equal to 2. So that verifies the third condition then for Rolle's theorem. So now let's find the values of c in the open interval that satisfy the conclusions to Rolle's theorem. Okay, we're verifying conditions, okay, and then finding all the c. So we had conditions, let's say that was part A. Let's find the values of c. So f of t is t cubed minus t plus 2. Okay, the conclusion is that f prime of c is equal to c, okay, for some value of c contained within the open interval from -1 to 1. That's our conclusion. Okay. So let's find out what our derivative is. Okay, f prime of t is 3t squared minus 1. Okay. So we can set that equal to 0 and solve for t. Okay, so we have t squared is equal to 1/3. And that has solutions where t is equal to plus or minus the square root of 1/3, or plus or minus the square root of 3/3. So there are two values of t that make this statement true. We should say for c, right? So f prime of c equals 0 when c is equal to plus or minus root 3/3. That's we have c is equal to root 3/3 and c is equal to negative root 3/3. Okay, c needs to be contained within this interval from -1 to 1. Are these both contained within that interval, or is only one of them in there and the other one not? Okay, we should verify. All right, so the square root of 3 is approximately 1.73. So the numerator is less than the denominator. So this fraction is therefore less than 1. And this fraction is going to be greater than -1 for the same reason that this one's negative. Okay? So both of them are contained within the interval. Okay? So c can equal either negative root 3/3 or positive root 3/3. In fact, we wanted to find all the values of c such that the statement was true. Okay? Those are the values within the open interval from -1 to 1. That satisfies Rolle's theorem. So for another type of exercise with Rolle's theorem, state why Rolle's theorem cannot be applied to a given function on a given interval. So we're given the function f of x equals x to the 1/3 minus x on the closed interval from -1 to 1. Okay? So that is, for some reason we should be able to verify that f prime of c is equal to 0 is not a guarantee. there still might be values of c that the derivative of this would equal 0. There might even be such values within this interval. But Rolle's theorem guarantees for us that these values exist. Okay? So it's being suggested that we cannot guarantee that those values are going to exist. How do we show that? Well, let's check the conditions. Okay, the conditions are continuous on a closed interval. Okay, so we want to check to see if that's true. We want to check to see if it is differentiable on the associated open interval. Okay, and the third condition, we want to check to see if the outputs at the endpoints are in fact equal to each other. If any one of these three conditions, it only takes one, if any one of these is not satisfied, then therefore Rolle's theorem would not apply, so we could not guarantee the conclusion. Okay, so let's check those. First, continuity. Where is this continuous? Okay, f is made up out of two terms with different parts. Okay, so we have a part, let's see, we have x to the 1/3 and we have x, right? So we have its part radical, or root. Okay, that's the x to the 1/3 part, right, which is the cube root function. Okay, and an odd root function, okay, is going to be continuous on all real numbers, negative infinity to positive infinity. Okay. Now the other part, f is part polynomial. That's the other term. Okay, x. Okay, and a polynomial is also continuous on all real numbers. Okay, so since the given interval -1 to 1, okay, is a subset of, I could just write out is a subset of, or use that symbol, okay, is a subset of all real numbers, okay, then f is going to be therefore continuous on the closed interval from -1 to 1. And what about differentiable then? Well, let's see. So we have that the cube root function, okay, is the cube root function differentiable for all real numbers? Well, we can check and see. Okay, let's take a look at what the derivative is, f prime of x. All right. So the derivative with respect to x of x to the 1/3 minus x. So that equals 1/3 x to the -2/3 minus 1. Another way to write that is 1/3 times the cube root of x squared and then minus 1. So here's our derivative. And notice that f prime of x then, right, is not defined if x equals 0. Okay, not defined if x equals 0. Okay, and 0, okay, is contained within the open interval -1 to 1, right? It's a value within the open interval. Okay, so therefore f is not differentiable on the given open interval. Okay. Now, if f had a if f was not differentiable at some value, but that value was outside of this interval, right? Then, in other words, if f was still differentiable at least within this interval itself, then we would still be okay to use Rolle's theorem. But it's because we found a value where the function is not differentiable and that value was contained within the open interval, that's why this is not differentiable in that interval. That's why we can't use Rolle's theorem. And that's enough right there. So we can just conclude at this point, therefore, Rolle's theorem does not apply. Okay, the third condition doesn't need to be checked. We can't do Rolle's theorem. Okay, to the function f on -1 to 1. Now, okay, so we have, so that we can interpret this geometrically as well, as a refresher, right? We have the function y equals the cube root of x, which is defined for all real numbers. It's continuous for all real numbers. But what feature would the graph have such that it's not differentiable when x equals 0? If we take a look at the graph of the cube root of x function, okay, it comes up like this, okay, and it goes over like that. What's the feature we have right there? All right. It's continuous here. This is at the point 0, 0. So this is not going to be differentiable there because the tangent line would approach a vertical line. That is, we have a vertical tangent. And with a vertical tangent, the slope is going to be undefined. Okay? So we're going to have a discontinuity in the graph of the derivative. Okay, what kind of a discontinuity would we have in the graph of the derivative of this function? Okay, so now let's take a look at the mean value theorem, mean referring to average. So the mean value theorem is the one that states that if you have a function that is continuous on a closed interval and differentiable on the open interval, then the function must have at least one point in that open interval such that the slope of the tangent line is the same as the slope of the secant line over the entire interval. That is, that the average rate of change over the interval is equal to the instantaneous rate of change at least one point within the interval. Okay? And this picture gives us a geometric interpretation of that result. Now, in order to prove the mean value theorem, okay, we can use Rolle's theorem, but there's a third condition for Rolle's theorem, right? We still have the continuous and the differentiable. The values at the endpoints need to be the same. But the mean value theorem doesn't require that. So suppose that we have a case of the mean value theorem where we have a continuous and a smooth curve connecting two endpoints, but that the two endpoints have different y values. F of A and F of B are not necessarily the same value as each other. How do we get that third condition on this function to be able to use Rolle's theorem? Well, here's a technique we can use. We're going to be considering the slope of the secant line that connects those two endpoints. So let's create a new function that connects those 2 points, a linear function. So g of x here is just the straight line that connects those two endpoints to each other. Now what we can do to get that third condition for Rolle's theorem is, because these functions f and g connect to the same endpoints, we can take the difference between f and g to create a third function. Let's call it h. So h of x is, for instance, equal to f of x minus g of x. Or it could have been g of x minus f of x. Right? Because if we construct it that way, notice if we plug in a to the function h of a, well, that's equal to f of a minus g of a. But f of a minus g of a would have to be 0, because f of a and g of a are equal to each other. Similarly, if we plugged in b, we would get h of b is f of b minus g of b. But that also would equal 0. So in other words, h of a is equal to 0 and h of b is equal to 0. Therefore, this new third function called h of x is a function that would satisfy Rolle's theorem. Observe, is h of x continuous? Yes. Why is it continuous? H must be continuous because it is built up out of a difference between two continuous functions. F was already known to be continuous, right? We already verified that f was continuous before we did this construction. You have to state why it's continuous. Is g continuous? Yes, because it was created to be just a linear function. So a line is a type of polynomial, therefore it is continuous in all real numbers. So g is continuous. And when you subtract a continuous function from another continuous function, the result will also be continuous. Same argument for differentiability. F was already differentiable on the open interval, okay, presumably before we started this construction here of drawing the line. F was already differentiable, and since g is a linear function that is not vertical, then g is also differentiable. So if we wanted to know what is the derivative of h, we could find the derivative of h by taking the derivative of f and g and subtracting, right? H prime is equal to f prime minus g prime. Therefore, h is both continuous and differentiable. It's continuous on the closed interval, it is differentiable on the open interval, and as the third condition of Rolle's theorem, h of a is equal to h of b. Therefore, Rolle's theorem applies. Rolle's theorem applies to h, that is, that there must be at least one value of c in the open interval from a to b, such that h prime of c is equal to 0. H prime of c. Well, what is h prime of c? H prime of c is f prime of c minus g prime of c. And if h prime of c is equal to 0, then that means that f prime of c minus g prime of c is equal to 0. The same as saying that f prime of c equals g prime of c. That's the same as where f prime minus g prime equals 0. That's where we use Rolle's theorem there. So f prime of c must equal g prime of c for some value of c. The same value of c that would have made h, right, have a it would have made h have a horizontal tangent line. Now we don't see the picture of h. I didn't graph what h would look like. Okay, we're just we know that this has to be true by the theorem, and the fact that we know how to, for instance, to distribute the differential operator. Derivative of h is equal to the difference in these derivatives right here. Okay, so we've reached a conclusion that f prime of c must equal g prime of c. Now, what is g prime of c? G is just a straight line. It's a line segment, right? So, and a line has the derivative of a line is equal to the slope of that line, and the slope of the line can be found by doing the rise over run. That is, g prime of c must be g of b minus g of a over b minus a. Now, since g of a and g of b are the same as f of a and f of b, okay, then the slope of g is the same as the statement f of b minus f of a over b minus a. And that concludes it. That is, we have f prime of c is equal to g prime of c. G prime of c is g of b minus g of a over b minus a. But g of b and f of b are the same, and g of a and f of a are the same. Therefore, f prime of c equals f of b minus f of a over b minus a. And that, right, and that proves the mean value theorem. Okay. All right. So you have some exercises to apply the mean value theorem. Okay. Verify the hypotheses of the mean value theorem. Now there are only two hypotheses to the mean value theorem. Okay. Continuous and differentiable. So f is a combination of polynomial, a constant, and a rational function. Those three terms. So we know polynomials are continuous and differentiable for all real numbers. Constants are continuous and differentiable, okay, for all real numbers. And rational functions are going to be continuous and differentiable wherever they are defined. Right? A rational function is continuous on its domain and also differentiable on its domain. We learned that previously. So we need to know, well, what is the domain? At least for this term, that is the trouble term. Well, this term has a domain where x is not equal to 1. So, therefore, f, in entirety, f has a domain where x is not equal to 1. Okay? And since this term is rational, we also know, therefore, that f is continuous on its own domain. F is therefore continuous for all x's other than 1. And differentiable for all x's other than 1. Okay? Specifically because that relates to the term that was rational, which was the most restrictive of the three terms. Okay, so there is a domain restriction. Okay, x cannot equal to 1, but x equals 1 is not within the interval that we're interested in. So the mean value theorem therefore would apply. Okay. This we could have run into a problem here if this was an interval that did contain x is equal to 1. Let's say it was the interval from -2 to 7, for example. If it was from -2 to 7, we would want to be careful to not jump ahead to the conclusion of the theorem and start calculating what the slope of the secant line would have been, or the average rate of change over the interval. Right? If you imagine if it was from -2 to 7, then the theorem would not apply because the given function was neither continuous nor differentiable throughout that interval. But since x equals 1 is not even within this interval, okay, then the mean value theorem applies. That is, we can now find the average rate of change, f of 7 minus f of 2 over 7 minus 2. Okay, and that quantity, which I calculated here, is equal to 1/2, must be equal to the derivative of the function at least one location within the open interval from 2 to 7. So we can find out what f prime of c is by taking our derivative, f prime of x, plug in c. So here's our f prime of c, 1 minus 3 over the quantity c minus 1 squared. Set f prime of c equal to the average rate of change, which is 1/2, and solve the resulting equation, knowing that there must be at least one value of c that makes this equation true. So we solve the equation, we get c is equal to 1 plus or minus the square root of 6. And if we check numerically here, say the square root of 6 is more than 2 but less than 3. Because square root of 6 is more than the square root of 4, square root of 4 would be 2, but the square root of 6 is less than the square root of 9, and the square root of 9 is 3. So that's true also because the square root function is an increasing function. Otherwise, if you check on your scientific calculator for an approximation here, okay, point is, when you add 1 plus the square root of 6, you're going to get a quantity that's somewhere between 3 and 4. And quantities between 3 and 4 are contained within the interval from 2 to 7. So 1 plus the square root of 6 is a value of c that is in the open interval. And therefore, 1 plus the square root of 6 is a value that satisfies the conclusion to means value theorem for this function. That is that the slope of the tangent line to this function, at the point where the input is 1 plus root 6, the slope of that tangent line would be exactly equal to 1/2, which is the slope of the secant line connecting the endpoints. Now the other value of c we found from this equation here is 1 minus root 6. Again, you can check with your calculator. Again, if root 6 is between 2 and 3, then 1 minus root 6 is less than negative 1. It's between negative 2 and negative 1. And a number between negative 2 and negative 1 is outside of this interval. So we don't want to include that other value of c for this particular exercise, right? It's not in the interval of interest. Okay. Verify the conditions, continuity on the closed interval, differentiability on the open interval, state the family and where that family would normally be either continuous or differentiable. In this case, we have a composition, we have a natural log, and we have a square root function. Okay, so the square root function in the argument, the square root of x, okay, that's continuous for x is greater than or equal to 0. But when you take the natural log of something, the natural log is continuous as long as the input is greater than 0. Okay, so in a whole, this is continuous if x is greater than 0. And the closed interval from 1 to e is contained within the larger interval, okay, from 0 to infinity, the open interval from 0 to infinity, contained within that. Differentiable. The natural log function is differentiable within its domain. All logarithmic functions are differentiable within their domains. And the square root function is differentiable except at its endpoint. So therefore, this function is going to be differentiable for all values of x that are greater than 0. Okay, so the mean value theorem therefore applies. That is that f prime of c for some value of c in this open interval from 1 to e must be equal to f of e minus f of 1 over e minus 1. And so you can go ahead and solve this. You find the derivative, you can plug in c, so you get 1 over 2c, that's f prime of c, and you calculate the average rate of change over the interval, which is 1 over 2 quantity e minus 1, and solve this for c. You get c must equal e minus 1, approximated here, okay, in our geometric interpretation. Maybe try another example here. F of x is equal to x squared over x plus 1. Okay. On the interval from 0 to 1, closed interval from 0 to 1. So to start with, we have conditions. The first condition, is this continuous on the closed interval 0 to 1? Okay. Well, f is made up of a combination of polynomial over polynomial. That is that f is a rational function. So f is a rational function where x is not equal to negative 1. Rational functions are continuous on their domains. Okay, so as a result of this, okay, f itself would be continuous, okay, on all real numbers except negative 1. So from negative infinity to negative 1 union negative 1 to infinity. And furthermore, the interval 0 to 1, okay, is a subset, okay, of the domain of f. Okay, so f is continuous on the closed interval from 0 to 1. It's a similar argument for differentiability. Okay? So we have that f is differentiable on 0 to 1, right, since the family f is rational function where x is not equal to -1. Okay, another way to make this statement right here about subset, okay, is to say, and since -1 is not an element of the open interval 0 to 1, so we have that it's rational, okay, and we have that that value is not contained within an interval, okay, then f is going to therefore be differentiable on the open interval from 0 to 1. So therefore the mean value theorem applies to the function f on the closed interval 0 to 1. And now we can apply it. Conclusion of the mean value theorem is f prime of c is equal to f of b minus f of a over b minus a. That's our conclusion. Okay. So find the values of c such that this would be true. Okay, so f prime of x is derivative with respect to x of the function x squared over x plus 1. So we can find this derivative with the quotient rule. So we have low times the derivative of the high. So d high is 2x minus the high, which is x squared, times derivative of the lower function. Okay, the derivative of x plus 1 is just 1, and that's over the quantity x plus 1 squared. I'm going to want to clean this up because we're going to be solving an equation with this expression in it in a moment. So let's see. So we distribute the 2x, we get 2x squared plus 2x minus x squared over the quantity x plus 1 squared. Combine like terms in the numerator, I get x squared plus 2x over quantity x plus 1 squared. So f prime of c equals c squared plus 2c over c plus 1 quantity squared. And that's the left-hand side of the conclusion of the mean value theorem. On the right-hand side, we have f of b minus f of a over b minus a, where b is equal to 1 and a is equal to 0, because we're on the interval from 0 to 1. Okay. All right, so this is to be equal to f of 1 minus f of 0 over 1 minus 0. All right, because that's our f of b minus f of a over b minus a for this example. All right, so c squared plus 2c over c plus 1 squared. Okay. Function f was x squared over x plus 1. So f of 1 is 1 squared over 1 plus 1, which is going to be 1/2, minus 0 squared over 0 plus 1, that's just going to equal 0, over 1 minus 0. Right, so this is equal to 1/2 minus 0 over 1, which is just 1/2. So we're solving the equation c squared plus 2c over c plus 1 quantity squared is equal to 1/2, and we're solving that in the open interval from 0 to 1, right, because that's where we have differentiability. So I'm going to solve this start by cross multiplying. So we have 2 times c squared plus 2c is equal to c plus 1 quantity squared. That's 2c squared plus 4c is equal to c squared plus 2c plus 1. So we have a quadratic equation here. I'm going to move all the terms over to one side for our quadratic. So subtract c squared from both sides, subtract 2c from both sides. And I'm also going to subtract 1 from both sides so that we can set this equal to 0. So we have c squared plus 2c and then minus 1, and that's equal to 0. Solve this quadratic equation. Does not look like it factors, okay, because I can't find two integers that multiply to -1, but that add up to 2, and the leading coefficient here is 1. So I'm going to use the quadratic formula then, or completing the square would be fine as well. By the quadratic formula, we have c equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 1 all over 2 times 1. So that c is equal to negative 2 plus or minus the square root of 4. We got a minus 4 times negative 1, so plus 4, so the square root of 8. Okay, and this is all over 2, so I'm going to put this over 2, this over 2. So we get negative 2 over 2, which is negative 1, plus or minus the square root of 8, which simplifies as 2 root 2, and then that's over 2. So we get to cancel a 2 there as well. So I have c is equal to negative 1 plus or minus the square root of 2. Okay, now the square root of 2 is greater than the square root of 1, but it's less than the square root of 4. The square root of 4 is equal to 2. The square root of 1 is equal to 1. It's between these two. No, it's between these two because the square root function is an increasing function, right? F of x is an increasing function. So if you increase the input, you would increase the output. That's the definition of increasing function algebraically, right? If you increase the input, x2 is more than x1. For an increasing function, that would also result in an increase in the output. All right. F is increasing. So if x2 is more than x1, then f of x2 will be more than f of x1. So I'm saying if I increase the input, if I change 2 to a 4, the output, the square root of 4, would be more than the square root of 2. So this is helpful because without a calculator, I can already estimate. I know that the square root of 2 is some number between 1 and 2. In fact, it's about 1.414. But the square root of 2 is between 1 and 2. Right? I used the same justification earlier with the square root of 6, saying the square root of 6 is between 2 and 3, because 6 is between 4 and 9. So anyway, so this means we have two quantities here, right, to consider. Negative 1 plus root 2, and we have negative 1 minus root 2. Maybe I want to call that C1 and C2, for instance. So since the square root of 2 is between 1 and 2, then C1, that's negative 1 plus root 2, right? If we just subtract 1, and subtract 1, we would get negative 1 plus root 2. Well, that would have to be between 0 and 1. All right, so C1 is between 0 and 1. So C1 is contained within the open interval 0 to 1, which is the interval we were working with. C2, okay, we have negative 1 minus root 2. Okay. All right, so since root 2 is between 1 and 2, then negative 1 minus root 2 is going to be between what? Negative 2 and negative 3. So between negative 3 and negative 2. Okay, so C2, okay, is contained within an interval between negative 3 and negative 2. But that is not between 0 and 1. Okay, so for the values of C that we just saw for here, C equals negative 1 plus root 2 is the one that is contained within the interval 0 to 1. Hence, C equals negative 1 plus root 2 is the only value that we found that satisfies the mean value theorem for the given function f on the closed interval 0 to 1. Okay, so for these exercises, verify the conditions. When it's stated in the instructions, they're going to verify the conditions. How do you verify? Check to see what family you're working with. Okay, in some cases you're going to have multiple families to consider. Like you have something that's part polynomial and part exponential, part logarithmic. All right, for instance, this was entirely a rational one. That is a ratio of polynomials, specifically, ratio of polynomials. If this were something like x squared over the square root of x plus 1, that's not rational. Okay, that's a combination of functions. You can call it fractional. Okay, but there, if it was x squared over the square root of x plus 1, you'd want to consider what is the domain of x squared, which is all real numbers. What is the domain of square root of x plus 1? That would be where x is greater than or equal to negative 1. And then for the combination, the denominator can't equal 0 as well. So you want to find what is the domain for that combination and know for that family if that is a function which in general is going to be correct for us in general, if that family is one which is continuous on its own domain. And most of the functions we work with will be continuous on their domains. So it usually comes down to looking at the domain to determine where it's continuous. Okay, so stating what the function is. And verifying that the interval that you're given is contained within that domain. We can expect it will be, but we need to check to see that it is. So the function that it is, okay, what is the domain of that function in general, okay, and a statement that says, but any issue of that domain is not contained, is not within the interval itself, or the interval itself is completely within the domain of the function. For differentiability, you want to know where is the function differentiable, and that can come from knowing what type of function. If it's polynomial, you know it's differentiable everywhere. If it's rational, it's differentiable anywhere within its domain. Same for trig functions and log functions, for example. Okay. But more generally speaking, if you can calculate the derivative, find f prime as find f prime symbolically, you can then check to see, well, what is the domain of the derivative in order to establish where is it differentiable. Okay, to establish where it's going to be differentiable in general. Okay, so this function is rational, which is differentiable wherever it's defined. So our function is differentiable as long as x is not -1, and then again, but x is not going to be -1 for this example because the given interval didn't include -1. For Rolle's theorem, you have a third condition to check, and that third condition for Rolle's theorem is that f of a and f of b must be equal to each other. After that's done, then you can go into the conclusions of the theorem. For Rolle's theorem, the conclusion is that f prime of c is equal to 0 for some value of c within the interval. For mean value theorem, it's that f prime of c is equal to the average rate of change over the interval. In each case, you have to find the derivative, and then you're either setting the derivative equal to 0, or you're setting the derivative equal to the average rate of change, depending on which theorem you're using. And then you're solving the resulting equation algebraically. Okay, you've done the derivative, now you do the algebra. Now check your answers. Check your answers to see, first, are they the correct answers? And second, are those answers in fact contained within the interval that we were interested in? Okay, only accept the answers that are actually contained within the given interval. All right, and that should take you through the homework. I mean, one other thing here, again, we talked about geometrically how we can interpret the answers. Right, the geometric interpretation, for instance, for this answer is that this is from the mean value theorem. The derivative of the function x squared over x plus 1 at the input value, -1 plus the square root of 2, okay, that derivative would be equal to the slope of the line, okay, connecting f of 0 to f of 1. Right, so the average rate of change of this function over the interval 0 to 1 is the same as the instantaneous rate of change of this function at the point where the input is -1 plus root 2. Okay, so you can interpret it in terms of instantaneous and average rate of change. You can interpret it in terms of the geometry, the slope of a secant line, the slope of a and the slope of a tangent line. Okay, and if it were an application problem like with like position, velocity, acceleration, you can also interpret it within the context of the given function. Okay, that's it for this section, and that also concludes the content that is going to show up on your next exam for this course, which is really revolving a lot of the applications we have for derivatives. If you have any questions, you can let me know. Take care.